Hey guys, this is Stephen Mossberger with a school exclusive. Let's go ahead and talk a little bit further about this product development, very crucial document called the Safety FMECA. This is our number one document that is of the utmost importance to our product development. This one and the system FMECA is kind of everything that is required to know to kind of do just the basic of product development, and this is also the core of all your product development, and will also dictate when you're when your product is ready. So let's go specifically in this video talk about the safety FMECA. So what is a safety FMECA? So FMECA is a failure mode. So F is failure, M is mode, E is effect, and critical analysis. So basically, the key to this is the critical analysis. For this, you have to be very imaginative, very creative on different ways that your product can fail. One of the ways that you can easily do it is assume that your product is not safe and assume that everything can happen and prove that it won't happen. Give yourself a reasonable, when I say a reasonable doubt, like a very high reasonable doubt that that will not happen. So let's say that you have a car and you're worried about your brakes coming undone. Let's say your upper or lower control arm is coming off. And you say, okay, well, what are all the different ways that the upper and lower control arms can come off? Oh, they can come unbolted. Okay, well, how do I make sure they don't come unbolted? Okay, well, I have cotter pins, I have castle nuts, and things like that that hold it in, or I have, press fit, all these retainer rings and all these different things, or press fit, to hold it as well as something else, as well as a castle nut and cotter pin, and all this Loctite and these things, and also mark it to make sure that it's not been tampered with, all these things, right? So, and then you say, okay, without a reasonable doubt, I highly doubt this will become undone. So if I highly doubt it will come undone, I give the severity a low number. So it's a very high number, but the occurrence, the probability is near zero, right? Anyways, so let's go ahead and talk about how this kind of works. That would be kind of the thought process, is be very creative on all the different ways that your product can fail. And because this is a safety FMECA, we're mainly looking at two things, either equipment damage or personnel harm. So in this case, I'm mainly talking about, in this one, I've separated other FMECAs that I've seen have had both in here, equipment and personnel. And this, I'm talking specifically focus on personnel safety. So the hardware safety and also process and uptime and things like that we'll cover in the system FMECA. But in the safety FMECA, we'll talk about 100% personnel. So how do I keep personnel that is interacting with my product safe? And what would that look like? So how you would fill this out, I can go ahead and jump to my examples, talk about how to fill this out. So this is an example, and you can see here that these are the rules, right? So basically, SOD of above 100. So SOD is the severity times occurrence times detectability. And if it's above 100, you need a mitigation. And then if severity is above or equal to 4, you need a mitigation. So whenever you have one of these change, for some reason not changing. Why is it not changing? Anyways, you can see, oh, because I'm in the wrong, this one. I'm in the wrong account. That's okay. So let me go ahead and switch the accounts over here. Okay, let's go ahead and bring it back. So yeah, so when you go in here and you enter 4, it'll turn red, right? If it's below 4, it'll turn green. So if you have any red on here, you need to create a mitigation. So let's talk about that. So here, if it's above 4, it requires a mitigation. So what is a mitigation? A mitigation is something that you will incorporate to lower either the occurrence chance or the severity of something happening. So, and I can talk a little bit about that. Also, increase the detectability. So, basically, decrease the amount of different things that can happen. For severity, it's mainly going to be some sort of design changes to lower the chance that this thing has a problem. So let's go ahead and take a look at some of these examples. So here's an example, and then we can go over also the rating, which is the second sheet here. So possible failure modes, effective safety incident, potential causes of safety event, and then controls. What controls are you integrating currently, and then also what is your mitigation plan for controls that you're adding. So for example here, these are basically some examples here of some of the personal things that I worked on. I will keep adding to this over time as we go along from different projects or different videos that we do. So for example here, heater exposed contact. So basically, what if you had and it happened on a project that I'm still currently working on, but early on in this project. So there's a tiny little exposure of a bare metal contact that we have 208 live voltage coming to on this heater. And so we need to make sure that personnel cannot touch that and then touch, something else. So let's say that we have this small two-way contact and you can touch it. It is within personnel contact. So how would we prevent this from happening? So one of the things that you can do is you can pretend that this is before. So we have, heater exposed contact. So let's go here and let's just right click and I'm going to say insert one column above. So let's say heater exposed contact before above controls. So we could say effective safety incident, personnel shock and short. So basically cause maybe a fire, personnel touching, right? This one, and then we could say or starting electrical fire. Oh, personnel touching, live wiring, or shorting. And then you want to be pretty descriptive here on this. I wasn't so descriptive here. So, you know, you want to be as descriptive with this as possible. So when you show somebody else in your team, they kind of understand what you're talking about. So here, personal shock, shorting, short causing personal injury or fire. So that's basically what can happen. So here, let's say let's say that we have none. So let's say we have none. We have none. This is basically this is easily accessible. Somebody could touch it. There's no PPE, no nothing. Obviously, severity is high. I mean, we can go with the rating, right? But here, rating, right? Electrical, fatality, burns, or disabling injury from shock, right? So this could kill you, right? Obviously, with this is again all of these FMECAs. Most likely, you could not be a safety engineer. So most of these are to your best ability. What do you think? Your honest answer, regardless of what happens to the project, because your projects that you develop, most are possible to kill somebody. So be very serious about this, right? So this could kill somebody. 208, high voltage. This particular thing had a 10 amp breaker on it. So you're putting, 3,000 watts power, right? So this could cause some serious damage. Actually, I think this is a 15 amp circuit before it would trip. So it could dump 15 amps circuit, 15 amp to you. So actually, the only thing it really had was a ground, right? That's all it had. So all it had was a ground, right? So that makes severity high, occurrence relatively low. Let's just put a 1. We can talk about the occurrence before. Actually, let's say in this case it's like exposed, so you can pretty easily touch it. Detectability that it'll cause a shock. So this one, I would probably, because this has 2 detectabilities. So here it would be, okay, personnel shock or short. So let's insert a row above. So this would be another good example. So we would go here and we would say, okay, well, we're going to break this into two pieces. So we're going to break this apart. So here we're just going to talk about. So again, this one we're going to keep in there because we want to talk about, um, hey, fires can kill people, right? So if we go here, we can go look at the rating, right? We can have um, different fires and things like that happening, right? So here, ground breaker. So we're gonna say this is a 10. It could kill personnel. Occurrence is gonna be low. We can look here at the occurrence. So occurrence rating, not reasonably foreseeable occurrence. I would say this is probably a possible occurrence, right? So this is possible occurrence is between 0.04 and 0.2% of the time. So this is a possible occurrence that somebody can get a nice little zap, depending on if they have glove PPE. In this case, this example was in semiconductors, so I mean you're wearing gloves, you get a little bit of an insulating layer. But let's say that this is a 6. So detectability, how can you tell that this is on? I mean, there's no, let's just say that we didn't have any stickers, things like that. So detectability is kind of lowish. There's no alarms, no flashes, no nothing telling you that this thing is hot, right? Um, with the existing control methods, there might be a risk that the failure will not be detected, right? So here with the existing control methods, basically there is none. So I would say this is like a 5 or 6. So altogether here, it looks like I didn't put the this one. So here it has the suggested. So there you go, 300. It's above 100. I need a mitigation. So this is my mitigation. Take this, put it here. So now tool guards with interlock covers present. So basically I have to use some sort of tool to remove an interlocked cover that has a switch to disable the power to the heater. So that if I touch the heater, it is not possible to get shocked because there's never a power to that heater with that interlock in place, right? Assuming the interlock's working. Electrical hazards inside. So OSHA stickers, so you could have danger, high power, the alert type thing. Let's see. So you'd have something like this, right? This is the most common. So you'd have something like this, right? Danger, hazardous voltage enclosed, right? You'd have something like that. Anyways, so electrical hazard side OSHA sticker fixed to cover to warn of hazards. Warnings present in procedure. So inside your procedure, you say, hey, during your operation here, you could encounter high voltage. Make sure everything is shut off and that everything is locked out. And then you use lockout tagout to hold it off, right? So here you can say, lockout tagout. So here you could lotto the breakout, you could lotto the switch to keep it off. So I would say now this is like you've completely removed the severity of this happening, right? One, 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 one. I mean, it basically never happened. which is the same as above. So this would be how you would do a mitigation. So you see red, and now you fixed it. So then let's say you would have this as a certain phase, phase 3 prototype, and then phase for beta. This is what you would have, right? And then the next one, this would be up here, so you get rid of the red. So when your product is ready to go, it should have no red, and you should spend multiple weeks working on this, right? Finishing it, thinking of crazy stuff that can happen. Again, very, very creative. Anything that can possibly happen, prove that it can't happen. And if it can happen, figure out how to prevent it from happening by improving your product. And every time that you do that, and the more creative you are, the better your product is. Right? And I've had instances where me and my team have both not been creative enough in the past, and it's caused serious delays, millions of dollars of lost revenue, and things like that. So don't let it happen to you. Okay, so next one, shorting causing fire. Okay, so this is a big one, right? So this one, it could even happen even with this tooled guard. So we can say, hey, the severity here would be high. So we would say, let's just say here, ground breaker. Let's say that. So then let's say, severity is let's say 6. So here we go, the ratings, severity, right? We're talking about mechanical here, electrical burn, right? So we'd say it's like 6, 7. Let's say a 7. So let's say a 7, and then occurrence very unlikely. So let's call this 2. Detectability of fire causing here. I mean, you wouldn't really tell that. I mean, let's pretend that there's no cover, so you'd very easily tell it's a fire. So this would be 14, right? And this main page I already have where it's got the multiplication here. This has already got the multiplication loaded there, so you don't have to worry about that. So here, even though this is green, if this is red, you still have to have mitigation. Any red on the row, you have to have mitigation. So we're going to say here that we're going to have ground breaker, and then we're going to have, you can go crazy with it. You can go crazy with this. You can have, for example, for 3D printing, they have one of these discs that you put in there, and when it gets too hot inside, it will, you have electrical fire on the 3D printer, it'll pop this disc, and then it would put out the fire. Right, so you could have a fire suppression system, right? You can have an enclosed volume. So basically, it's difficult for it to get air, so it'll probably put itself out very quickly because it doesn't have very good access of air. And that's usually good because you have insulated this heater so that the heater is very efficient. It is not dumping heat into the environment. So you have an enclosed, very low air exchange rate that could be possible. So you're gonna starve the fire out. And then obviously you have a breaker, so if it shorts, it's only going to catch on fire initially and then put itself out because we will use fire retardant materials only used. And then you could have smoke alarms / interlocks. So when you have some sort of smoke detected, it shuts itself off. Another one is water leakage detector. So if there's water that drips on the contacts, it can't short the two together. If you have enough water there, it just shuts everything off. Things like this. Be very creative, right? So I would say here with this ground breaker fire suppressant system, enclosed volume, so starves fire. Fire retardant materials only used. Fire retardant approved materials. Smoke alarm interlock. Water leakage detector interlock. Right. So there, I would say, I mean, this pretty much makes it nearly impossible that it kills this one. So even if the breaker doesn't trip and it's still supplying 2,000 watts of power into this fire, because fire retardants will only put themselves out if the energy is removed. So let's say the energy is not removed, the fire is still going. Let's say it doesn't short. then the fire suppression system would put it out, or the enclosed volume will starve the fuel of the fire. The fire retardant systems, well, the fire retardant material is used, so if it does indeed short, it'll put it out. And if none of those work, the smoke alarm interlock will kill the power. And then a water leakage detector interlock will make sure somebody didn't drip water through the top of the this guard, and it now is dripping down in there and keeping shorting everything out. So those are some mitigations here. You can look here at the hot surface at heater. So personal burn with no PPE, melting of flammable plastics, chemical VOCs, hot surface, tool guard with interlock cover present. Switch to disable power to heater. When removed, thermally hot surface hazard inside. OSHA sticker fixed to cover to warn of hazards. You saw that one. It would just say hot surface and have a plate with these little squiggly lines coming out of it to represent a hot surface. Warnings present in procedure of hot surfaces, prompts on systems showing that components are hot. So this would be, I would say, a high chance of having problems, severity of burns, right? Depending on here, in this case, it's just a 90C. So, I mean, you have to keep your hand there for a while to get a severe burn. So that's using this rating here of a 4, right? So we would say injury, but not disabling, right? It just hurt for a while, but not disabling. So add flashing LEDs when the lid is hot, increasing flashing when lid present interlock is removed to tell the operator the hazard, right? Also, you can have in the software, all this kind of stuff. So now I would say 3111. So now we have a 3, right? Because even if this shuts off, it will still be hot, but I think this probably 3 is a little on the high end. Probably the chances are like 2 or 3 that someone actually disregards all of these warning signs and still puts their hand on the thing, right? And so let's talk about some of these mitigations that we're using here. So this is in the design for a product, the product procedure, product development procedure. So let's talk about this. So design for systems, design system to minimize risk, Safety FMECA scorecard, which is basically this. This is a Safety FMECA scorecard. Tools shielding, right? So this is basically design. This is the number one thing that you can do. Tool shielding, use minimum aspects of system that can cause safety concerns. So if you only need 60C, but for whatever reason you're doing 90C, drop it down 60C. Less chances. Chemicals, do you really need those chemicals? All these mechanical components, do you really need them? If not, get rid of them. The noise, radiation, etc. Have safety devices. So incorporate safety devices, interlocks, de-energizes things when certain situations are satisfied. So basically, you remove a lid, you remove a tool cover, shut off the power, shut off things moving, shut off radiation, shut off chemical, shut off mechanical, shut off thermal, shut off all the hazards, right? Shoot for hardware interlocks where possible. Sometimes, generally, the rule is hardware interlocks are number one. If you can have them, have them. But there are some situations where hardware locks cannot exist, and only software locks inside your control system can exist. Uh, that obviously software interlocks are better than no interlocks at all. Ideally, it's best to have both. If your hardware interlocks are like some sort of extreme situation, so that it doesn't interrupt. And again, all of this safety is obviously to not. The idea is to have your product be as safe as possible, but not have the safety features cause false positives and disrupt your process. So that's kind of the balance, right? So generally in that case, your hardware interlocks are usually at an extreme case scenario. So if you have like a thermal runaway, it's at like maybe the very end of what your heater can go to, right before you have damage. Now, generally, it would be great if you had software interlocks that would catch the problem before it hits the hardware interlock and maybe some damage to the equipment happens, but you save the personnel, right? Save the machine if you can, right? So warning devices, warning lights, flashing, prompts in the software, error codes or hazard codes, like I said here, noises, sirens, horns, beepers, things like that. Vibration, any sort of haptic feedback, anything like that. hazard labels, stickers that state the hazard, pinch areas, hot, electrical, etc. Bare minimum is the stickers have to say that you assume risk by going past a cover, usually on a tooled or non-tooled cover. So basically, high voltage contained inside, high temperature contained inside, pinch hazards contained inside, right? And then another one, safety devices. Another example here for hardware and locks, Lotto would be another good example. All right, so let's put here example Lotto. So Lotto is pretty good. Lotto means lockout, tag out. So develop procedure on how to prevent an incident. This is generally the first and worst line of defense because you basically want to pretend like the customer has never seen this procedure before. But they are great to have. They will save you in a lot of accidents. This is generally the first and worst line of defense, but this line of defense will prevent a lot of incidents. Main reason for this is it prevents personnel from accidentally exposing themselves to more risk than the action that is needed. So basically, let's say you only need to remove this cover to do something, and to do that, let's say it needs to be energized, right? So if you don't have a procedure, maybe the customer accidentally opens this other let's say you just were looking at a mechanical component. Let's say they take out the wrong cover and now they expose themselves to radiation or noise or chemical or thermal that they if they had a procedure, they wouldn't have exposed themselves to those hazards. So basically, only expose yourself to the hazards that you actually need to expose to get the equipment back up. Obviously, for customers, it's best to have that not happen. But this is also for your personnel. I mean, maybe for this again, this is more than just product development. This could be also for development of your tool that you use on site for manufacturing things. So this is how you would design it as well, right? So only have exposure to things that that you need to have exposure to. If you don't need to have exposure to it, then it is not needed, right? So make think about that. Anyways, having all kinds of manuals, operating manuals, preventive maintenance manuals, any sort of maintenance manuals, repair manuals if you have somebody doing repairs, etc. Even for your team, right? You're not just protecting your customer, you're protecting your team. Anybody interacting with your tool. PPE. So this is good to have if needed. It can be great protection, but this is the worst level. Main reason is that there could be the user's not wearing it, or some sort of person walking by doesn't have it, and they get caught in something, and now you've just exposed them to something else that didn't need to happen. So this is the Safety FMECA. Go ahead and check it out. It is linked inside of the classroom, inside the hardware development resources, in the school group. Go ahead and check it out and let me know what you think. I'll catch you guys in the next one. Later.